Let's get started. This is Carolyn Maher-Boulis, and she's from Lee University in said Cleveland, Tennessee. And she wants to share with us her experiences with three modeling projects in differential equation. Caroline, I'll turn it over to you.
Thank you, Ryan, and thank you for allowing me to present my experience, and thanks for all of you who are attending this presentation. I've come to know of SIMIODE years ago, and when they actually even had like their first website, and I thought it was a great resource for teaching differential equations. I love having the scenarios, the real life scenarios for applications and implementation in the in the course. So I've taught differential equations so many times. The last 2 years is when I started actually implementing these projects into my classes. I've adapted some of SIMIODE's scenarios to use in my classes. So in this presentation, I'm going to share 3 modeling projects that I have used in the last 2 years, how I administered those applications, what criteria I used to select the applications, how I adapted them. All 3 I've adapted them, some in very small ways and some in larger ways. And I adapted them based on my population of students. So and then the rubric, I'm going to share the rubric I use for grading, and finally just give some feedback from students' course evaluation at the end of those 2 years when I administered those applications. So I assigned these scenarios from SIMIODE as projects in the classroom. They were not done in the classroom, but in the course. I will give the students a week to work on the project, and I would talk a little bit about the project, kind of give them an introduction of what the project is about, what they're expected to do. And for 2 of the 3, they actually have to do an activity and collect data. You'll see that in a minute. And I broke up I broke up the projects into parts. So if it was a long project, I broke it up into parts so students don't get overwhelmed with the many steps and the different questions that I have. So they were assigned a project outside the classroom. We'll talk about the project a little bit in the classroom. They are allowed to work in groups if they wanted to, or individually if they preferred to. But most of the students like to work in groups, and the groups range from 2 to 3 students, but not more than 3 in the group. I chose the scenarios based on these criteria. First of all, I wanted it to be something fun for the students that they can relate to and understand. They're not intimidating. They can see with simple differential equations how the applications are powerful, and give them an appreciation of differential equations. I didn't want scenarios or projects that would implement different tools in different disciplines. So I have something from sciences, I have something from biology. I actually tried to find something for finance because we have actuarial students in our department, but I haven't found one yet. And meaning that there might be one out there, but for me to adapt it or to work on it, to use it in my classroom, maybe required more work that I was able to put in at that time. But in SIMIODE, in CUBE's hubs now, where they're keeping all these scenarios, I like that you can actually search by discipline and the type of differential equation very much. So that's possible, and makes things easier, better than the previous website where they had all these scenarios. And of course, I wanted things to be easy on me to grade also. So those were the criteria upon which I choose a scenario. And the three that I used last 2 years were within that range of, or satisfied this criteria for me. The first, these are the three modeling scenarios that I've used. I'm using the titles used by SIMIODE, mixing it up, modeling populations with death and immigration using M&Ms, and modeling ICU spread. Mixing it up is a chemistry, excuse me, it's an application in the chemistry discipline. It's about separable differential equations. Modeling with M&Ms is life sciences, and it's linear differential equations. And all of these are first order. And modeling ICU spread, also separable, but in health sciences. So I'll talk about each one of them a little bit, and then talk about the rubric. So this is the exact statement of this scenario. I always start with this project because it's simple. The SIMIODE version actually has like 3 questions like this, or 3 parts into the project or to the scenario. I only took the first part. So we're given an amount of salt, initial amount of salt dissolved in some quantity of water, and then water entering the tank at a certain rate with a certain concentration. Excuse me. And then it's leaving the tank at the same rate. And there is several questions to this part: building a differential equation, in solving it, and then answering some questions. SIMIODE has different, has this, and has, I think the next iteration or the next part of this project is the rate of the incoming rate is different from the outgoing rate. So I didn't want to include all of that as a first project for the students. I just wanted it simple, something that they can do, and something that will make them appreciate the application of differential equation. So there was a small adaptation, very, very small adaptation to this, in addition to just removing the other 2 parts in the scenario. I just added this part C in red, draw a graph of this function on Desmos. So through the projects, I tried to get them to use graphing calculators or graphing tools in Excel, so that they get some of these skills along the way without me having to actually teach them. So that's the first one. I always start with something simple like this. That's what I've used in the first 2 years. This semester, I'm actually teaching differential equations again, but I'm going to change that first application, and I'm going to use a potato cooling scenario, which is similar to this. It's simple. But students are actually going to heat up a potato and measure the temperature and collect data themselves, instead of just getting this information without and then solving. But it's the idea is the same. It's going to be separable. They have to collect some data. It's probably going to be in parts. I'm going to break the project in parts to make it simple for them, or one step at a time, take them one step at a time. But at any rate, this was the first project that I used in the first 2 years. Second project, modeling with M&Ms. I give students each group, I give them a bag of M&Ms, a plastic cup and a paper plate. And then they collect data in this experiment. So they shake the M&Ms in the cup and throw it out onto the plate. And then the M&Ms with the M side up, they represent dead people. And so they take it out from the pool. And the ones that lie on the blank side, they are lives, they go back into the cup to the next iteration. So they do this, they do the experiment several times. And before they collect the data, they have to answer some questions. And the questions get them to think, what do you expect is going to happen? There are people dying all the time, and you have a finite number of M&Ms or a finite number of people living. What is going to happen? What are the assumptions? And then after they answer these questions and get their mind thinking about it, they run the experiment and then collect the data. And then they are asked to compare the results of the experiment with their answers to the first set before they actually run the experiment. That's the first part of that project. So the project is longer, but I break it up to several parts to guide the students one step at a time through it. Part two, they are walked through building a model for this first simulation, which represents death only. So they're putting aside all the M&Ms with the M site up. And so, of course, the population is decreasing. Eventually, it's extinct. And they build the model, the differential equation model, and then they're compared to ask they're asked to compare the results of their theoretical model with the actual data. In this way, I'm introducing them to the concept of error, or how to determine that if their model is actually a good fit to the real life scenario. Part three of this project is broken into 4 parts. They are walked through similar steps to parts 1 and 2, except now they're putting back immigration, or there's the immigration factor. So after they shake the M&Ms and set aside the ones with the M site up, they're actually going to add 10 M&Ms, new M&Ms to the living M&Ms. And so there's an immigration factor into this part. And they go through the same or similar set of questions, as I said, as in the first 2 parts, for parts 3 and 4. So that's kind of a long project. So they take about probably 3 weeks a month into doing this second project. The third project is ICU spread. So students are given a data set of voluntary nonprofit hospitals in the US with ICUs during the period from 1958 to 1974. And again, they're asked to graph the data set, to analyze the graph before fitting any model into it. And I asked them to search the internet to see or to learn about logistic differential equations. And give an argument why I give them a logistic differential equation. This is not something I cover in class. We don't present logistic differential equations and talk about it. But they are it's of a type that they have seen before, so they should be able to give some argument as to why this differential equation will be a good fit for this specific problem or for this specific data set. And they write an initial value problem that represents this scenario, and then eventually solve the differential equation and answer further questions. So these are I haven't adapted this much, this particular activity. The most adaptation I've done was in the second project about the M&Ms simulation. This is the rubric that I use. So each project is graded out of 5. And I do let the students know what is expected of them, with all these definitions of what is a well-executed submission, what is a well-communicated submission, and so on. Is this something that I took from you, Brian? I'm not sure. Is this something that you shared with us?
Yes.
Okay.
Yes, it comes from the Air Force Academy the year I was there, so I liked it.
Yeah, and it worked well for me. Yeah. So this is some of the students' feedback. We teach differential equation once a year only, and I've not had a negative comment about using the projects. Actually, these are all the comments that I got, and they're positive. One student said the examples of application to the real world using models was an aspect of the course that students that I found engaging for my learning. That's one student's comment. The projects that we did at the beginning of the semester helped establish more meaning to the computations. So maybe spend a little more time in class explaining why the methods of solutions are useful and in what context we might see them again. I really enjoyed the projects. I struggled to care about many of the types of differential equations we had to solve until I saw how they were used in an applied area of math or science. And the last one, I wish we had more project grades. I don't know if that because they didn't get a good grade on the project or they wanted more of those easy grades. It was not clear what this comment really referring to from my end. But that's I felt positive from the student comments, and that's what motivated me to just continue to do this. And my plan is if I can add one new project every year I teach, or every time I teach the course, then I'm happy. And I think the students will see a more benefit to the course than just going through a list of tools on how to solve these equations when they don't see where they're coming from or where they can see them. I think that's all what I have. Do want to thank Brian for all the work that he does with SIMIODE and all the team that's behind the scenes with us, and for all of you for coming to this presentation. And I'll just open the floor for questions if anybody has any.
Yeah, we're small enough that, just speak up if you have a question or a contribution. We welcome that. I know you're not shy because you're all adventuring in modeling.
Caroline, Caroline, thank you very much for that. I'm Kerry. It's really, I think I've lost. No, you're back again. Really nice. Thank you very much for sharing your projects. I'm just in the process of developing a modeling and differentiation course for our year 2s at the moment, and it was really nice. I was thinking about using the M&M problem because I'd come across it at our earlier teaching, and then we'd parked it, but you've just convinced me that we should bring it back, and that's what we should do. And it's really lovely to see your adaptations to it as well, so thank you very much. Just general comment. It's nice.
Well, thank you. My stock in the M&M company just went up. I appreciate that.
I was going to say, I used it based on Brian's suggestion. That's always, it's something very welcome, especially because students also get to eat them after they do the experiment.
Yeah. I mean, I'd seen that done at a teachers' conference actually by Anthony Harradine, and he'd done that and used it as a way of introducing the exponential decay model for secondary school students. Yeah.
Good. Thank you, Carrie. Any other questions? We've got a good time here. I wanted to ask, how hard was it to make this your own, Caroline?
I would say of the whole thing, grading and deciding on the scenarios to use takes some time, and especially going through all what's available. No, I don't go through all of what's available, but I mean, I search with some criteria, but then still have to read the ones that I think are doable, or the things that I can use. Having those LaTeX files to adapt the scenarios helps a lot. Those are the 2 steps that would take time: deciding on a scenario to use and then adapting it. So I've been for a couple of weeks now trying to adapt this potato cooling scenario. How do I present? Because I have to think, how do I want to present it to students? Am I going to break it into parts? And what do I want the first part to tell the students? And then what is the second part? and where to make the break, and just the logic, the flow of the different parts together, so that by the end of, if I do break it into parts, by the end of the project, they have a coherent picture of the scenario. So those are the two things that just take time. So that's why I said, like, if every time I teach it once a year, if every time I teach it, I introduce one new project, I'll be happy.
Okay. So searching for them, although we're trying to make it useful by topics and course, and then just modifying the LaTeX code for your needs, those are the two steps.
Right.
Okay.
And I do have to say that with the new Cubes Hubs capabilities, it's much easier than
Yes.
before.
Yeah.
I mean, there are a lot of scenarios there. So
Yeah.
when putting in the criteria, there's like, if I wanted a first order, and if I wanted a specific type of equation and a specific discipline, that's putting a lot of constraints to, but it provides, I mean, it does the job. Like, if there's nothing with the constraints that I have, then there's nothing. But if there are 5 or 6, I have to go through picking which ones.
Yeah, okay. I must tell you that the M&M Death and Immigration, I started when I was at West Point. Actually, I did it before, but I was in charge of the course, and there were like 900 cadets in the course, and every one of them, their instructors bought M&M's bags, and I really should have had stock. But right now, I imagine there are generals in the Pentagon around water coolers going, "Did you do that M&M stuff, that crazy stuff?" And so it sticks with them, as well as the calories if they eat too much of them. But
Yeah. I had students after the course like, "We want a snack. Do you have M&Ms in the office?"
Okay, there are variations that you can make. You can use dice, in which case the rule for death might be different. If you roll a 1 and a 2, you die. If you roll 3, 4, 5, and 6, so the binary 50% death rate, it can change. And another thing is that you can have each student decide their own immigration rate, collect the data, and then share that with a partner in the class and see if they can figure out what the immigration rate was based on the data that they got. So, and one other thing I wanted to say is you always ought to try out, anytime you're going to do something like with a potato, you ought to try out before you go to class. I've learned this from experience when I did a dry ice and the sublimation of dry ice. And I hung the dry ice over the scale by a contraption, and the cold carbon dioxide fell onto the scale, and the scale collected rime or wet ice. And so I had students in the class collecting the data. This is at Rose-Hulman, where Kurt and I taught together. They were collecting the data, and they were saying, "Dr. Winkle, the mass is going up." And I, in my typical New York style, said, "Just shut up, I don't want to hear that, and everything." And sure enough, I said, "Let's put the data on the board." They put the data, and they said, "See, it went up." And then I turned to the class, and I couldn't figure it out on the spot. I was nervous and everything. But the students quickly pointed out, because you could see the ice on the scale that was forming. So we had to collect a data set. That, by the way, that led to a more complicated model, but we didn't pursue it. But I had to collect the data set again. So always practice them. And even when you practice, you never know what's going to happen. So.
Right.
Any others, questions or sharing experiences with trying some experiment in class or? No?
Hi, sorry, can I ask a question?
Sure.
Hi, Caroline. Thank you for your talk. So I was wondering about your last project where you were using the logistic function. Are you doing regression to the data? Are you trying to feed the logistic model to the existing data?
Yes, so I actually give them this, let's see. here's that, can you all see my screen?
Yes.
Okay, so here's the that project, and they're given this data set, and then I give them the model down here and ask them to interpret what the parameters are, and then write it as an initial value problem. So what is the 100 mean? What does the 100 mean in this equation? What is the parameter R? And so on. And so they eventually solve it. So solve the initial value problem, and then they see if it fits the data that they're given, the solution.
So the parameters, they guess the parameters or based on the data, or because
I think the question is how much parameter estimation are you asking the students to do?
right. Thanks.
So can't remember if I asked them to do an Excel, because you, Brian, you do it on Mathematica, is that right? Or did you talk actually doing in Excel?
I've done both myself.
both.
But yeah.
I honestly can't remember what I did last year.
Okay.
Yeah, because I think you're right. You're right, Caroline. Because the thing is, they can guess the carrying capacity because that's the maximum of the data, how far it goes. The rate might be a bit more difficult, the intrinsic rate to figure it out. But if they do regression, then they get the estimated parameter values. So I guess either way, it's a good approach maybe to go through both. First guessing it, I know.
Oh, okay. Yeah. Well, one thing is you try to get the data in some linear form to do easy regression, or on Excel you can do nonlinear. But our time is just about up, and we got to move on to the next session, which is a keynote. So let's thank Carolyn very much for her
Thank you.
efforts. And I know all those people whose names are the only thing I can see are applauding vigorously. So I'm going to leave. If you want to stay and talk, that's fine. But I need to get on to do the next keynote. Thank you very much, Caroline.
Thank you, Brian.
Okay.